to introduce Mariya Soskova. She was a student of Barry Cooper. She got a PhD from Leeds. Moved back home to a job at Sofia University, and currently she's visiting Berkeley for a couple of years. She's going to tell us about the Turing universe in the context of enumeration reducibility. And I know some of you are hardcore red meat computability theorists, and enumeration reducibility is something that you'd be familiar with. But if you're not, I just wanted to say that it's something that goes back quite a long way. The enumeration degrees, under a different name and with a slightly different viewpoint than the modern viewpoint, were introduced by CiE as far back as 1952. And so they're a very natural structure. They've been studied for many years. I don't think they get quite the attention that they should, but today they're going to get quite a bit of attention. So, Mariya Soskova.
Thanks. First of all, I'd like to thank the program committee for selecting me and giving me the opportunity to speak here. This has special meaning to me because the first conference that I ever went to was also the first CiE conference in Amsterdam. And it's been a great pleasure to be part of this community. Okay, so I'll talk about the theme of the talk. The underlying concept of the talk is relative computability, or finding a way to compare objects in terms of their information content. And right from the start, we're going to agree that these objects are going to be sets of natural numbers, just because using sets of natural numbers, you can represent a large variety of objects that are of interest to us. But still, so now the question becomes, how can a set of natural numbers be used to effectively define a set of natural numbers A? And still, there's not just one way to make this precise. I will talk about two ways in which this can be made precise. The first one is the one that is most widely used. There is an algorithm which determines whether an element X is an A using finite information about memberships in B. And then if you use this approach, you get Turing reducibility. But another approach, and an approach that has been used by many people, in particular a lot by the group in Sofia, is the following. There's an algorithm which enumerates instances of memberships in A from instances of memberships in B. And in this case, you get enumeration reducibility. Now, I'm going to try to, in this talk, justify why the Sofia group uses the second approach. And I'll give 3 examples, which I think clarify why this is so, and show that using the second approach gives you a little bit more intuition and a little bit more insight into what's going on. But before I can do this, I will have to talk about these definitions in more detail. So let's start with the first one. So there's an algorithm which determines whether an element X is an A using finite information about memberships in B. First of all, what is an algorithm? Well, an algorithm could be a Turing machine, or it could be a program written in any common programming language like C or Pascal or whatever your favorite language. Or, because it is essentially a finite object, it is a finite sequence of instructions, it can be coded by a natural number. So we're going to think of these programs as computing functions from the natural numbers to the natural numbers. And by CiE, we just represent the program which, the function which is computed by the program coded with E. Okay, and now we're going to have to say what we mean that we use finite information about memberships in B. Well, these algorithms are going to be allowed during their execution to consult an oracle. So now and then they're going to be able to ask the oracle, does this particular element say 5 belong to you or not? And the oracle is going to answer yes or no. And this additional information is going to be used in the program itself. And so now we have CiE with subscript b. This is going to denote the function that is computed by this program, coded by E, when you use precisely b as the oracle set. Changing the oracle gives you different functions. And finally, A is Turing reducible to B if and only if the characteristic function of A, which is the function that for every n gives you 1 if n is in A and 0 if n is not in A, if this function is computable using oracle B. If this function is computing using one of these programs, so for some E, with oracle B. Okay, let's see some examples. What can you compute in this way? Well, for example, every computable set, so for any set of natural numbers B, every computable set is going to be Turing reducible to B, because for computable sets, you just need the first part of this procedure. You just need a program. And it doesn't have to make any queries to the oracle, so whatever the oracle is, it's going to have the same output, and it's always going to be the same set B. What else? Well, you can compute B if you have B. And the program is going to be very simple. So the program, immediately when it sees the input, the number n, it's just going to ask the oracle, does n belong to you? And whatever the oracle answers, it's going to output the same answer. So the relation Turing reducibility is reflexive. And also, if you have two programs, C is computed using oracle D and D is computed using oracle B, then you can combine the programs together to get that C is computed with oracle B. So the relation is also transitive. So these are positive examples of things that are reducible to each other. What about a negative example? Well, we have the Houting set, now relativized to B. This is the set of all numbers n such that the program with code n on input n halts with oracle B. And this set is now going to not be Turing reducible to B. And to see that this is true, my favorite proof of this is by Jeffrey Pullum. He shared it with us last year at the CiE conference in Cambridge as a present for Turing's birthday. It's a lengthy proof, but very poetic, and the gist of it is, imagine we have a procedure called P that for specified input permits you to see whether specified source code with all of its faults defines a routine that eventually halts. Well, the truth is that P cannot possibly be, because if you wrote it and gave it to me, I could use it to set up a logical bind that will shatter your reason and scramble your mind. Okay. Now let's move on to talk about enumeration reducibility. Okay, so there's an algorithm which enumerates instances of memberships in A from instances of memberships in B. Now the setup is a little bit different. Now we have a program that is running continuously, and it is enumerating numbers, well, pairs of a number and a finite set. This can be represented by one number, of course. So in essence, this is a CiE set, a computably enumerable set. At the same time, we have the oracle set, which is revealing its elements one by one in some order, and the order is not known or fixed in any way. And from these two procedures, so we have one procedure here, the axioms are getting enumerated, and another here. And we're observing these, and from these two, we are going to create one new enumeration. So we're combining both enumerations into one. If we see an axiom xt, and all of its elements have been enumerated by the oracle set, then we enumerate x. And we denote this by WE of B. And so A is enumeration reducible to B if A can be enumerated in this way for some algorithm or computably enumerable set, WE. Okay, let's see some examples here. So let B be, again, any set of natural numbers. What can we enumerate from it? Well, first of all, every computably enumerable set can be enumerated in this way. We just, again, need the first part of this procedure. We don't even have to look at what B is telling us to enumerate a computably enumerable set. Or if you like, we can replace the finite set D there by the empty set for any computably enumerable set. Again, we can enumerate B using Oracle B. The CiE set in this case, the axioms are going to be 0, singleton 0, 1, singleton 1, 2, singleton 2, and so on. And this procedure combined with an enumeration of B will produce exactly B. And in this case as well, we can combine enumerations to get the relation is transitive. Okay, these are again the positive examples. We want to get also a negative example. Well, if you consider the immediate analogy of the halting set, but for this setting, the set LB consisting of all elements n, such that n belongs to the nth computably enumerable set applied to B, well then we won't get a negative result because this set is going to be enumeration reducible to B. And the reason for this is that we have a universal CiE set. So things are not exactly the same as in the case with Turing reducibility, but they're not too different because if you take the complement of this set, so the set of all elements n which do not belong to the nth CiE set applied to B, then this is not enumeration reducible to B. And the proof is not too different. For imagine we have an enumeration called E, which outputs a P only if you see the Pth program with Oracle B will not in our lifetime enumerate P. Well, then E2 cannot be, because if you wrote it and gave it to me, I would make you seem foolish. I will not be kind, with a trick I learned from Cantor, and always keep in mind. Okay, so in any case, both of these reducibilities are reflexive and transitive. And we have now a standard method of transforming this into a partial order, which we call a degree structure. Okay, first of all, we define the equivalence relation. From the pre-order, we define equivalence relation. A will be equivalent to B, either Turing or enumeration, if and only if A is reducible to B and B is reducible to A. And the degree of a set A is going to be the equivalence class of A under this equivalence relation. Then we order the degrees by the obvious partial order. The degree of A will be less than the degree of B if and only if A is reducible to B. And we have, in both cases, a least element. For the Turing degrees, the least element is the equivalence class of the empty set. For the Turing degrees, it's going to consist of the computable sets, and for the enumeration degrees, it's going to consist of the computably enumerable sets. In both cases, we can define a least upper bound. So the least upper bound of the degree of A and the degree of B is going to be the degree that has the degree of A join B. A join B is a set that codes in its even elements the information from A, and in its odd elements the information from B. And in both cases, we can define a jump operation, which takes a degree to a strictly higher degree. And for the Turing degrees, we use the halting set. For the enumeration degrees, we use the analog of the halting set, but joined with its complement. Okay, so in both cases, we have an upper semilattice with least element and jump operation. And we already saw a flavor, got a hint that both structures are similar, but not quite the same. Let's see what the connection is exactly. Well, it's given by this proposition, which has an intermediate step. So if A and B are sets of natural numbers, then A is Turing reducible to B
if and only if both A and the complement of A can be enumerated by a computable and B function, or in other words, A joined the complement of A is CiE and B, if and only if A joined with the complement of A is enumeration reducible to B joined with the complement of B. So here it becomes clear that Turing reducibility uses from the oracle both positive and negative information and produces both positive and negative information. And enumeration reducibility just uses the positive information to get the and outputs the positive information. So how can we, okay. So this gives us the connection, and in particular, the first and the third part gives an embedding of the Turing degrees into the enumeration degrees. And this embedding is defined in the following way. It maps the Turing degree of a set A to the enumeration degree of A joined with a complement of A. And this embedding preserves the least upper bound, preserves the order, the least upper bound, and also the jump operation. So, right, let's define the images of the Turing degrees under this embedding as the total and call them the total enumeration degrees. So we have that the Turing degrees as an upper semilattice with jump operator are isomorphic to the total enumeration degrees, which are substructure of the enumeration degrees. And in this case, I say the Turing universe in the context of enumeration reducibility, because enumeration reducibility provides a bigger world of which the Turing degrees are part of. Okay. So the Turing degrees are a substructure of the enumeration degrees, and we have some more connections that show that they're a very important substructure. Salmon showed that enumeration reducibility can also be characterized in terms of Turing reducibility in the following sense. A set A is enumeration reducible to B if and only if the set of total enumeration degrees above B is a subset of the set of total enumeration degrees above A. So what this means is if you have a total degree above B, it has to be also above A. And this characterizes enumeration degrees entirely. And this means that the total degree, so the images of the Turing degrees, the image of the Turing degrees, is a very important substructure because it is an automorphism base for the enumeration degrees. This means that if you have an automorphism and you know how it acts on the total elements, then you automatically know how it acts on the whole structure. And a second connection is Soskova's jump inversion theorem. This is a very specific, small phrasing of it. It's much more general. And here maybe it's not even clear why it's called a jump inversion theorem, but anyway. It shows that if you restrict your attention to just the image of the jump operator, so you don't care about the original structure, but you care about what happens once you apply the jump operation once, then in both cases you get the same thing. So for every x, there is a total enumeration degree above it, such that both x and this total enumeration degree have the same jump. So if you just look at jumps, you don't get anything new. It's the same. Okay, so now I'll move on to my first example, and it comes from computable model theory. So let's fix a countable relational structure with domain the set of natural numbers. All our structures will have domain the natural numbers, even if it's not said. And suppose that you want to somehow characterize the information content of this structure. Well, what describes the structure entirely? You can take its atomic diagram. You can take the positive and the negative atomic facts. And from this contains all the information. But the problem is that this structure can be presented in some specific way so that just the way that these relations are formed appear as sets of natural numbers together codes more information, and there's some noise, some extra things that are not essential to the structure, but are essential to the presentation. So if you want to actually characterize the information content of the structure, you are going to consider all possible isomorphic presentations of A. So Richter defined the notion of degree spectrum of a structure A, and this is the set of Turing degrees of the diagrams of structures that are isomorphic to A. And if this degree spectrum has a least element, then it is the Turing degree of A. And we can think of that, we can argue that the Turing degree of A actually contains the information content of the structure. But it happens, and we will see an example of this in a minute, sometimes that this degree spectrum does not have a least element. So the information is not organized so nicely that this degree spectrum has a least element. It's somehow spread out. So Jokos suggested that for cases like this, one might look at the jump spectrum of A, and maybe, right, consisting of the jumps of the elements of the degree spectrum. And maybe now this has a least element, in which case it will be called the jump degree of A. And of course, you can iterate this. You can consider the jumps of the elements of the degree spectrum, and so on, to get the second jump degree spectrum, and so on. But we'll stop at the first iteration of the jump. OK. A concrete example. So a torsion-free abelian group of rank 1 for us is just going to be a subgroup of the additive group of the rationals. And I said that my structures are relational, so here, when I write plus, I mean the graph of the function addition. So suppose we want to understand what the degree spectrum of such a group looks like. We need some way to characterize the common information between isomorphic copies of a group G. And for this, we turn to a classical result by Baer, who introduced the notion of a type of a group G in terms of the divisibility properties of its non-zero elements. The precise definition is a little technical, and I will not get into describing it now in full detail. But what's important is that two torsion-free abelian groups of rank 1 are isomorphic if and only if they have the same type. And also, every such type can be represented as a set of natural numbers in a standard way. And we're going to call this standard representation of the type the standard type of G. Furthermore, every set of natural numbers can be coded as a standard type of some group G. This takes a little work to show, and it was shown by Downey and Jokos, who, after all this work, managed to characterize precisely the degree spectrum of a group G as the set of Turing degrees of sets Y, which can computably enumerate the standard type of the group. So because of this point, let me see if I can put this point here. Now the question of understanding these degree spectra of these groups reduces to the following purely computability theoretic question. Given a set A characterized, let's call it the spectrum of A, which is the set of all Turing degrees of sets Y such that A is computably enumerable in Y. And Richter had already shown that there is a non-C set A such that A is C in two sets B and C, which form a minimal pair. So what this means is that if you take this set A and look at its degree, its spectrum, then, well, the only possible element that could be a least member will be 0, because B and C form a minimal pair. A minimal pair is exactly this. The greatest lower bound is 0. But on the other hand, A is not C, so 0 cannot belong to the spectrum. So there are sets A for which this set does not have a least element. But Coles, Downey, and Slaman proved that if you look at the jumps of the elements of the spectrum of A, then this set always has a member of least degree. And as a corollary, every torsion-free abelian group of rank 1 has a jump degree. Not always a degree, but always a first jump degree. And the proof of this fact uses a forcing construction of this least member. So a construction which is meant to build this least element of this set. And other than solving this problem, it doesn't provide much more information. Now, let's look at the same problem, but in the context of enumeration reducibility. So let's fix again a countable relational structure. And Soskova looked at enumeration degree spectrum. He defined this notion. So the enumeration degree spectrum of a structure A is going to be the set of enumeration degrees of positive diagrams of structures which are isomorphic to A. So we don't use the negative facts anymore. We only use the positive facts. And again, if this set of enumeration degrees has a least member, it's going to be called the enumeration degree of A. So it's a similar idea following the main theme that enumeration reducibility is concerned with positive information. And just as Turing degrees were embedded into the enumeration degrees, you can transform the Turing degree spectrum of a structure into an enumeration degree spectrum of a structure, sort of embed one idea into the other in the following way. So you want to add the negative information about the diagram of A. Instead of the structure A with just R1, R2, Rk, these relations, you're going to add for every relation also the complement. And then you get a structure which is denoted by A plus, or the total version of A, which is, which connects the notions of the degree spectrum, the Turing degree spectrum of A, and the enumeration degree spectrum of these A plus. So, the idea is essentially the same as the embedding of the Turing degrees into the enumeration degrees. So the enumeration degree spectrum of this new version of A with the plus will be exactly the image of the Turing degree spectrum of A under the standard embedding. Okay, and of course, A has Turing degree A if and only if A plus has E degree, and it will be the image of A. Okay, so now let's get back to our torsion-free abelian group of rank 1. First, let's note that the diagram of this group is going to be an enumeration equivalent to its positive diagram. So the positive diagram, the positive facts already contain all the negative information. Because if you know, because addition is a total function. So if you know that 5 plus 3 is 8, you automatically know that 5 plus 3 is not 0, it's not 2, and so on and so on. 1. Okay, so in particular, we don't have to add the plus in this case. We have that the enumeration degree spectrum of G is exactly the images of the Turing degree spectrum, the image of the Turing degree spectrum of G under the standard embedding. And we already know what this looks like in terms of Turing reducibility. And now using our connection, the 3 points that were listed a little bit earlier, we can transform this into the following way. So let's denote the enumeration degree of the standard type of the group by SG. Then the enumeration degree spectrum of G is going to be precisely the total elements, the total enumeration degrees that are above SG. So here, things become a little bit more ordered already, and we can reason about this with our tools. So first of all, by Selman's theorem, we know that the enumeration degree, the type of G, the type degree of G, it is completely determined by the degree spectrum of G, because these are the total elements above G. So in particular, if we want this set to have a least element, the only possibility is the type degree of G. No other element can be the least element of this set. And so the group has a degree, both enumeration and Turing degree, if and only if the type degree is total. And furthermore, we know what the degree is exactly. It's the enumeration degree. The degree is exactly the type degree of G. And finally, by Soskova's jump inversion theorem, we get Cole's, Downey, and Slayman's result immediately, because there's always going to be a total element above the type of G, which has the same jump as it. So there's always going to be a least element in the jump spectrum. So just by viewing this program in the context of enumeration reducibility, we understand a little bit more. We understand what's going on. We understand what's the reason for the group to not have a degree, and in which cases it does and in which cases it doesn't. We understand exactly what the degree is. We understand exactly what the first degree is. And also, we see that Cole's, Downey, and Slayman's result is just a special case of a much more general result, which is this jump inversion theorem for the enumeration degrees. Okay, so this was sort of like a warm-up example. Now we move on to a second example that has to do with the global properties of both degree structures. So suppose we want to understand these degree structures. We want to really get our hands on them and know what they are. We have to study them, and we have to understand various aspects of them. In particular, 4 of aspects in which we might be interested in that are basic are the algebraic complexity. So there are partial orders, so we want to know how complicated are they as partial orders? Can we embed other partial orders in them? And in both cases, the answer is yes, we can embed. Well, I guess for sure we can embed any countable partial order in them. And when we go to uncountable, things get a little bit more complicated. We saw that in Andrew's talk yesterday. The second point is, what is their theory, the strength of their theory? So both structures can be expressed in the language of second-order arithmetic. So second-order arithmetic is enough to allow us to talk about them. The question is, what about their theory? Is it a fragment of second-order arithmetic, or can we get the full strength also in reverse? And again, in both cases, the answer is they are as complicated as can possibly be. They're both, the theory is computably is isomorphic to the theory of second-order arithmetic, and the result for Turing degrees is by Simpson, and for enumeration degrees by Slayman and Wooden. The third point would be to understand first-order definability. So in the language of a partial order, what sort of relations can we define just from the structure of the degrees? And the fourth point will be to characterize the automorphism group of the structure. Are there non-trivial automorphisms? How many are there? And so on. And it turns out that in both cases, all of these questions are related very strongly. So this is particularly clear from the way that the Turing jump operator was defined. So it is a theorem of Shor and Slayman that the Turing jump operator is first-order definable in the Turing degrees. There is a first-order formula. This means that there is a first-order formula of Ij in the language of a partial ordering, so using only equality and less than, so that this formula is true of degrees, Turing degrees x and y, if and only if y is the jump of x. And you will say, oh, first of all, this is a very remarkable property, because the way we defined the jump was in terms of sets and in terms of programs and halting. And this is just a formula that only talks about the way that the degrees are aligned with respect to each other. Well, of course, you can use quantifiers and logical connectors, but that's all you're allowed to do. So you might say, well, okay, what is this formula? How can you define the jump in this way? And the answer is, well, it's not so simple. The proof of this definability fact comes in has two main ingredients. The first one is the definability of the double jump by Slayman and Wooden. And this comes out of their analysis of the automorphisms of the Turing degrees. And as is written in Shor and Slayman's paper, involves explicit translation of automorphism facts and definability facts via coding of second-order arithmetic. And the second ingredient is an additional structural fact that allows you to extract the first jump from the second jump, which involves a sharp analysis of Kumabe-Slayman forcing. So there you have it. You have structure, algebraic properties. You have second-order arithmetic, so the strength of the theory. You have automorphism facts. Everything goes together into proving this one definability result. And the methods used in these proofs are also very, very powerful, mostly variants of forcing. Remember, forcing is the method introduced by Paul Cohen to show the independence of the continuum hypothesis from ZFC. So very, very powerful methods go into this one definability fact, which is really, really exciting mathematics and very, very interesting to read. Okay, so let's see how this story goes in the enumeration degrees. Well, when we talk about the enumeration jump, first we have to be aware of the existence of these special kinds of sets. So they're originally called semi-recursive sets. That's why the title is semi-recursive, but later they're semi-computable in the definition. And they are essentially semi-computable, maybe represents them better, gives better intuition about them. So a set of, this is a definition, a notion produced by Jokos. A set of natural numbers, say, is semi-computable if there's a total computable selector function, which always gets two elements as inputs, always outputs one of them. And whenever it happens that one of the inputs is in A and the other is not, it will correctly pick the one that's in A. So it's only semi-computable. So you can't really tell what the elements of A are in this way, but you have a little bit of information. You can distinguish in some cases. Well, in fact, they're very, very far from computable. Jokos showed that for every non-computable set B, there is a semi-computable set A, which is Turing equivalent to B, such that both A and the complement of A are not C. So these semi-computable sets appear in every Turing degree, not just the bottom one. But in the enumeration degrees, it turns out that they have a very special, very important algebraic property. So Arsanov, Cooper, and Kalimulin showed that if A is a semi-computable set, which is not C and not co-C, so the complement is not C, then the degree of A and the degree of the complement of A form a minimal pair. And in fact, they form a minimal pair in a very strong sense. So for every enumeration degree X, if you join X, so if you take the least upper bound of X and the degree of A and X of the degree of the complement of A, then these two sets are a minimal pair above X. So their greatest lower bound is X. So they form a minimal pair in a very, very strong sense. And of course, it would be wonderful if we can revert this into an if and only if statement. So every pair of degrees which satisfy this property turn out to be an instance of a semi-computable set and its complement. Unfortunately, this is not true, but Kalimullin managed to find precisely the notion which does capture this definition. So he introduced this definition. A pair sets are K pairs if there's a C set W such that the cross product of A and B is a subset of W, and the cross product of their complements is a subset of the complement of W. We call them K pairs. He originally had a different name for them. But in our work, we kept calling them Kalimullin's pairs, so for short, K pairs. Okay, let's see some examples. Well, a trivial example of a K pair is A and U for any A if U is CiE. Just because the CiE sets W that will serve that is needed for this definition will be the whole set of natural numbers times U, and that's a CiE set. And that will work. Another example is, well, all the semi-computable sets generate a K pair. So if A is semi-computable, then A and the complement of A is a K pair. And this is the CiE set in this case. And Kalimullin showed that in this case, you get an if and only if statement. So pair sets A and B are a K pair if and only if their enumeration degrees satisfy this formula. So here we have a nice definable class of degrees and definable by a very simple formula. It is worth pointing out that K pairs are never total enumeration degrees. So this definable class consists entirely of new elements that are not images of Turing degrees, that are invisible in the Turing universe. And in fact, the only total degree below either of them is the least degree, so they're quasi-minimal. And a consequence of the existence of non-trivial K pairs and enumeration degrees is that the second ingredient, the structural property from Schwarz-Lehmann's definition of the Turing jump, fails in the enumeration degrees. So this means that there can be degrees with the same algebraic property in the Turing degrees. So, but also kind of, this statement is a little worrying because it means that we might not be able to use a similar idea to define the enumeration jump and the enumeration degrees. Well, fortunately, Kalimullin showed that we don't need such a complicated idea because, well, 0 prime can be defined as the largest degree, which can be represented as the least upper bound of a triple A, B, and C, such that A and B are a K pair, B and C are a K pair, and C and A are a K pair. So every pair of distinct elements is a K pair. And using this, a relativized version of this theorem, he got that the enumeration jump is first order definable in the enumeration degrees. Now, recently with Hristo Ganchev, we have found a different definition, which does not even use relativization. We showed that for every non-zero enumeration degree, U prime is the largest degree, which can be represented as the least upper bound of a K pair, such that one of the elements is below U. So whichever definition you pick, it is a real formula that you can write down. And, well, if you expand the definition of K, maybe 2 lines, but still a very, very feasible natural property defines the enumeration jump. Okay, and finally, the third example concerns the local structures. So we talked so far about global properties of the structure, but if you want to really understand things in detail and study them in great detail, you might want to zoom in and look at one interval of degrees and see what's happening there. And you might consider, to be more precise, an interval between an element and its jump, and again, to be even more precise, between 0 and the jump of 0. So the local structure of the Turing degrees is just the Turing degrees that are Turing reducible to the degree of the halting set. And the local structure of the enumeration degrees consists of the enumeration degrees below 0 prime. So remember that we mentioned that the embedding of the Turing degrees into the enumeration degrees preserves the jump. So in this case as well, this means that if you restrict it just to the local structures, you still have an embedding of one into the other. So the local structure of the Turing degrees is isomorphic to the total degrees below the first jump of the least enumeration degree, which is a substructure of the local structure of the enumeration degrees. Okay, so here, again, we can ask similar questions. In particular, we can ask what relations are definable. And we can't anymore talk about the definability of the jump operator because just one application of the jump already takes you at the top element or outside. But we can use the jump operator to define classes of degrees. In particular, a degree is going to be low if it has the least possible jump. So it has the same jump as the least degree. And similarly, a degree is high if it has the largest possible jump, the same jump as the top element. So its first jump is 0 double prime, which is the jump of 0 prime. Shor proved in 2012 that the high degrees are first order definable in the Turing degrees. And his proof actually is quite similar conceptually to the definition of the Turing jump. So first, he showed that the theory of first order arithmetic, now everything can be expressed in first order arithmetic. So this can be interpreted in the local structure of the Turing degrees. So again, the theory of the local structure is as complicated as it possibly can be. Then he showed that there is a definable way of mapping a degree A to a set A in any interpretation of arithmetic, so that the second jump of A belongs to, the second jump of the set A belongs to the second jump of the degree A. And from this, it follows that every relation which is invariant under the double jump is definable, and definable in arithmetic is definable in the local structure. And finally, an additional structural property, which was proved actually by Shor and Sleman earlier, gives you the definability of the high degrees. So I should mention that Shor's theorem follows the same ideas that were in Shor and Sleman's paper, but they were for a substructure for the CiE Turing degrees. And also that I phrased here the result in a simpler form. Actually, you can define a whole hierarchy, the low n degrees and the high n degrees. And the definability result is that the low n degrees are definable for every n greater than or equal to 2, and the high n degrees are defined for every n. But it's not known if the low degrees are first order definable in the Turing degrees, and that's still an open question. So now, with Christo, we wanted to start with the same kind of program for the local structure of the enumeration degrees. And initially, our initial motivation was just to prove the first part, to prove that the theory of first order arithmetic is interpretable in the local structure of the enumeration degrees. And Sleman and Wooden had shown that the theory is already undecidable. And our clever plan was to use their result, extend it using k-pairs, and we would get the interpretation of first order arithmetic. But the problem was that in order for our plan to work, we had to know that these k-pairs are definable locally in the local structure. But remember that the formula that defined them in the global structure is a universal formula. So it has a for all. Something has to be true for every enumeration degree, and it's not at all clear if it's enough just to ask that it's satisfied by just the ones that are below 0 prime in this little interval. Well, we still don't know if it's enough, but by adding an additional structural property, we managed to show that they are still first-order definable in the local structure. And because I keep mentioning these additional structural properties, I thought I'd write it out here, just to show you that the definition doesn't get that much more complicated. In any case, once we had this result, we were able to complete our plan, and we showed that the first-order theory of the local structure is computably isomorphic. So as complicated as it can possibly be, it's computably isomorphic to the first-order theory of true arithmetic. And secondly, though, this definability of the local structure unlocked our hands, so it kind of unraveled a puzzle of many definability results in the local structure, among which the most notable ones are extending a result of Georgi, Sorby, and Young. We showed that the low degrees are first-order definable, and they're definable by a very natural property. So an enumeration degree is low if and only if every degree below it bounds a k-pair. So again, a simple definition. And secondly, extending Djokovich's theorem, we showed that a degree is total if and only if it's the least upper bound of a maximal k-pair. So the class of total, the local structure, so the local structure of the Turing degrees is actually a definable substructure of the local structure of the enumeration degrees. So maximal k-pairs, it's an easy structural property. So you have k-pair. It's maximal if there's no k-pair above it. But it's hard to write down. OK. So this last theorem, of course, brought us back to an old open question. So we know now that the total degrees above the first jump of 0 are first-order definable. This follows from Soskov's jump inversion theorem and the definability of the jump. So above 0 prime, something is a total degree if and only if it's the jump of something. So it's in the range of the jump operator. We know now that the total degrees below 0 prime are also first-order definable. Well, is the whole set of the total degrees first-order definable? And this is an old question. It was said in Rogers. It's in his book from 1967. And it is an important open question because, if you remember, we noted that the total degrees form an automorphism basis for the enumeration degree. So a positive answer would connect the problems of the existence of non-trivial automorphisms in both structures. And here's one further step in the dream world, how wonderful it would be. Remember our alternative definition of the enumeration jump. Here it is again. Well, we notice that if we can extend our local definition of the total degrees, so if we could show that a degree is total if and only if it is the least upper bound of a maximal k-pair globally, well then it follows that we would also be able to define for total degrees the relation x is CiE in U. And the definition would be, well, x is CiE in U if x is an element of this set. And in this case, our definition of the jump would read, for total sets U, the jump of U is the largest total degree, which is CiE in U. And this makes this definition very, very natural, and on the other hand, gives hope that maybe there is a way to extend it. Unfortunately, we've tried very hard, and we haven't yet come up with a way to extend the definition to work for all enumeration degrees. And after trying very hard, I decided to look and see how much of the automorphism analysis can be applied in the enumeration degrees. So the proofs here work are a little bit different. On the one hand, it's much harder to code. Coding is much harder. So you always have at least one or two quantifiers more to deal with. On the other hand, things are simplified by the fact that we do have a natural definition of the jump, where Slemon and Woodens analyzed the automorphisms to prove the definability of the jump. But in any case, some results are the same. For both structures, the Turing degrees and the enumeration degrees, there are at most countably many automorphisms. We don't know if there are two, but we know that there can be more than countably many of them. Every automorphism is arithmetically presentable, so they're easily described. There is a finite automorphism base, in fact, consisting of just one element. One element determines the behavior of the automorphism on the whole structure. And from this, we get that the definability with parameters. So every relation that can be expressed in second-order arithmetic and translated to a relation on Turing degrees, so it has to be degree invariant and definable, of course, in second-order arithmetic, is definable in the degree structure with parameters. And as a corollary from this, we get that the total degrees are definable, but with parameters, one parameter, actually, in the structure of the enumeration degrees. So one parameter away from a full definition, which makes it even more desirable to find out what the answer is. This is all. Thank you.
Are there any questions for Mariya? Yes?
In the total degrees, you have this phenomenon whereas you go from, say, many one reducibility up to the hyper degrees and so on. You get a kind of progressively tighter grip on the structure as you go up. Has anybody looked at that kind of phenomenon in the enumeration degrees, or is that something that's still to be investigated?
That has still to be investigated, and that's very interesting to see. In fact, I think that enumeration degrees fit within this hierarchy. So I think it starts at the many one degrees, goes through Turing, and then enumeration degrees, and on to arithmetic and hyperarithmetic. So they're one of the nodes in this chain.
More questions? You get to have the microphone.
Okay, one more. I've often heard Dana Scott say people should study the enumeration reducibility more. Now, he's in no way interested in degree theory or core recursion theory. What's he getting at? Have you found out yet? Why is he interested in enumeration reducibility so much?
Well, he's interested in them because enumeration operators provide a model for lambda calculus, and he's interested in lambda calculus, so that's why he thinks that enumeration degree should be studied more. But he is actually interested in these results as well. At least he goes to talks about them.
Any further questions? Oh, yes.
Just if you look at this aspect of enumeration reducibility using positive information only versus Turing reducibility using both polarities. Now, in learning theory, there is also this difference between using positive information only or positive and negative examples. Has there ever been any attempt to bridge those two fields, applying one IDs from one field to the other, as far as you know?
As far as I know, Actually, I don't know much about learning theory. I'd like to learn some. That's why I come to these meetings. And maybe Frank will know if there's been any attempt. Well, maybe that should be discussed afterwards. Thanks for the question.
Are there more questions? Okay, let's thank Mariya again.